A vector is defined by a magnitude and a direction. We talk about the direction being an angle. In actuality, the direction is the direction that the vector is pointing in. Basically, a infinite line that goes on forever that represents the direction of that vector. Usually, if we have a fixed set of axes, there'll be a fixed angle associated with that direction. But sometimes we want to use standard axes. Sometimes we will use rotated axes. If, for example, we're dealing with a ramp and we're traveling up and down a ramp, it makes more sense to align our axes with the slope of the ramp rather than the slope of the ground. So notice here that these two vectors are the same. I can pick it up here, and you can see that even though they look a little bit funny, they're the same vector. They're just being defined off of different axes. So if I want to find the components of this vector with a magnitude of 4 and an angle of 60 degrees, that 60 degrees is defined as counterclockwise from the positive x-axis. I can find the components of this vector by drawing a vertical line through the tip, a horizontal line through the tail. Those give me my vector components. Those vector components are in the direction of the axes, and implicitly there's an I hat and a j hat unit vectors that are defined in conjunction with using our standard axes. And so my I hat is the x direction, that's this component, the j hat is the y direction, that's that component, so I can find ax and ay. We've seen how to do that. We've seen that ax, the x component would be the magnitude of the overall vector times the cosine of the angle. And ay is the magnitude of the vector times the sine of the angle. In this case, this is the reference angle, the angle inside the triangle, but the way this is defined, it's the same angle there. So my x and y components here would be 4 cosine of 60 degrees and 4 sine of 60 degrees, because again, this is my a, the magnitude of the vector, this is my theta, the direction of the vector. I can find values for those two, and they're both positive. The x direction is positive because I'm pointing to the right. The y direction is positive because I'm pointing up. So I can take this vector here. I found the components, the x component and the y component, and so I can express this vector in component form by saying it's 2 in the x direction, represented by the I hat, and it's 3.46 in the y direction, which I represent with a j hat. So these would be the components of this vector using our standard axes with our standard I hat and j hat vectors. Now let's say that I have this exact same vector, but instead of using my standard axes, I want to use rotated axes. So with these rotated axes, implicitly, there would be an I hat prime, a new I hat and a new j hat that would be unit vectors. They still have a magnitude of 1, they still have no units, and they still point in the x and y direction, but the x direction is now this direction, the x prime direction and the y prime direction are now in different directions because the whole thing has been rotated, in this case, 30 degrees counterclockwise from where we started. And so we want to express this same vector, but we want to express this vector in terms of these new coordinates. So to define this vector, we find the components the same way we did over here. We draw a vertical line through the tip and a horizontal line through the tail. The difference here, though, is how we're defining vertical and horizontal. This is vertical. Vertical is aligned with the y-axis. This is horizontal. This is aligned with the x-axis. So in fact, I draw a quote-unquote vertical line through the tip, a quote-unquote horizontal line through the tail, and these will be my components for the same vector, but measured from the new axes. So this would be like ax prime, and this would be ay prime, the new x and y coordinates that I have there. These are still at a right angle, so I still have a right triangle. And in this case, I know that the original angle, the original definition of the angle, was 60 degrees. I know that this is 30 right here. This whole thing is 60, so this has got to be 30 degrees there's left. So I have the magnitude of the vector, and regardless of what axes you use, the magnitude of the vector should be the same either way because it's one vector. The direction of the vector should be the same as well. These two vectors are identical. They're pointing along along parallel lines, but the direction is different because the vector hasn't changed, but the other side of that angle has changed by changing the orientation of the axes. And so we have to find a new direction. We haven't really changed the direction of the vector, but we've changed the way the direction is measured, and so that changes the angle there. But now I still have a magnitude of the vector, I still have a direction, and I still have a right triangle, and so I can still find my x and y components. Here the primes just mean the new value of that variable, right? It's the new x and the new y. So in this case, ax prime is going to be the magnitude of the vector. The magnitude of the vector is still 4. It's still the same vector. The angle is now 30 degrees instead of 60 because of how far we rotated these axes. And so now this is going to be 3.46 in the x direction. This is going to be 2 in the y direction. And I would write this now as I hat prime and 2 j hat prime. So the primes tell me that these are the are relative to the new axes. The vector A is still vector A because the vector itself hasn't changed. So you can take the same vector and have x and y components relative to your standard axes. You can have the exact same vector that you have, but you have new components relative to rotated axes, rotated at any angle. The magnitude of the vector should be the same no matter what. The direction is basically the new angle. The new angle is going to be the difference between the original angle, the angle relative to the original axes, and the angle of rotation, how far we have rotated these angles by. If we rotate clockwise instead, and we rotate x double prime, let's say, and y double prime in that direction, we still have the same vector that we have before, but now we have the original theta plus the angle phi. But basically, you just have to convert, if you have the vector, you want to convert it into polar form, into magnitude and an angle. The magnitude is going to stay the same. The angle you have to adjust based on the angle of rotation. And then once you have the magnitude and the new angle, you can find the new x and y components the same way that we found these before. We will be rotating the coordinate system pretty regularly, particularly when we're looking at forces. And so being able to convert, find the components of a vector either in a rotated frame or in your standard horizontal and vertical frame will be a very helpful skill for you to have.